So, I've always been confused why in a setting like this, where we have like let's say a ball, let's say we have like a balance, and we try to draw like a force diagram, but we draw three forces, and I've always not really understood why we have to draw three forces in this diagram. And here's one of my biggest misconceptions is that, well, if there's like two forces downwards that we draw and one upwards, does that mean if, let's say, the resultant force is zero, well, it is zero because this is in equilibrium right now, does that mean like the n downwards plus the mg downwards equals to n upwards? And it's definitely not the case because, well, the n's are equal right here. But why would there be like two normal reaction forces? And if there are two normal reaction forces that are like a pair, why would there be an mg? So I think sometimes if you're thinking in the same way as what I just described, you're looking at the force diagrams wrongly. And that's not the way you actually interpret this kind of diagrams. So in order to read like a force diagram, you have to look at individual bodies, or I like to call them individual systems. So one way to look at a diagram is when we call like the entire thing a system. That is, let's say the ball plus the balance is one system. We could say that this entire system is in equilibrium, which means that obviously the resultant force equals to zero. But also we can break it down into individual components. And let's say we only look at the ball, or we only look at the balance. I also like to call it systems, and maybe this ball is a system by itself, and this box is a system by itself. And this is actually not a box, it's a balance. And okay, back to my question. Why do we draw three forces in this diagram? Well, in this diagram, obviously I've drawn out all the forces that are in play. However, this does not mean that, does not mean that the mg plus n equals to n, because that's not the way we look at it. So let me just go through the forces one by one. So firstly, the mg right here, this body, or this ball, I should say, is having a certain mass, and this mass will always press down on whichever surface that it's landing upon. So even if it's like on a hill, it would exert like a mass of mg. That one is constant, and there's just no way to change it. However, we also have our action-reaction pair over here, and this one I'll explain the upward force first. I think this one is quite obvious. So since the ball is pressing on the balance, the surface of the balance right now, there will also be a force to counteract or to exert on the ball, because if we don't, the ball keeps sinking down into the balance. So there has to be a force that counteracts the force of the ball by pushing it back upwards. So this is a normal reaction force, or the contact force we're talking about here. However, we also draw this another n force that's acting downwards, and that makes up our action-reaction pair. Usually I don't really understand why we have like another normal reaction force, but now I try to understand it as not the force that the ball exerts on the balance, but the force that the balance actually experiences. So if our force right here, let's say if our force right here if we're talking about like the ball acting on like this balance, let's say if we call this force like the force acting on balance, oops, by the ball or mass or the body. If we call this the force acting on balance by the ball, then I'd call this normal reaction force that's counteracting with this one. I call this force the force actually felt by the surface. I know this might seem a little bit stupid, but I don't think there's a better way to understand it, at least for me. And for me right now, I just have to kind of get it, what's going on here. So I've created an analogy. I'm gonna attempt to draw it out. So you can also try this yourself. So use your left hand and your right hand. And now you can place your right hand horizontally like this. Let's say this is your wrist. And you can put it like in a position that where this is your thumb. Your hand can be just like laid out like this. It requires a bit of twisting of your hand, but you can try this. My drawing's a bit bad, but yeah, I hope you understand what I mean. This is your right hand. And now use your left hand and just clench it into like a fist and put it down onto your right hand, like on the palm. And your hand with your thumb pointing this way, it will look something like this. And again, my drawing will be pretty bad, but I hope you understand what I mean. This will be your hand. And to be clarified, this is your nails. Like this. And this is your fist, by the way. So you can try this. Now, use your left hand to push down on your right hand. So you'll notice that your left hand is exerting a force onto your right hand. And, oh, by the way, this is in equilibrium. So this whole thing is in equilibrium. If you don't, because I'll just explain later. Equilibrium. So what that essentially means is that, well, even though your left hand is pushing down your right hand, your right hand has to exert a force that's equal and opposite to your left hand. So only that way your arms are not going to move and it's going to stay in one place. I'm just going to redraw this whole thing again, but like a little bit simpler. This is your left hand. This is your, let's say, your right hand. So the left hand, now, let's say if I push down, I'm going to exert a force that's called by left hand on right hand. A downward force. And let's just say if my right hand does nothing, it's gonna feel a force coming from the surface of my palm, like from this part. From the surface of my palm, or just my palm, because like the palm is the surface of my hand. So from the palm, you're gonna feel like a force that's acting downwards. Your palm is gonna feel a downward force if I do nothing. And so this is actually the normal reaction force we drew like up here. Wait, up here. This is a force I'm talking about. Wait, let me use a different color. It's a bit confusing. So this is the force, actually, acting down. What did I say just now? Okay, this is the force felt by palm of right hand. And since it's felt by the surface, I can call it a contact force. I mean, I can just call it that way. But since right now I have a condition right here that my system must be equilibrium as a whole, so my right hand shouldn't be just falling lower and lower. Hence, this is why my right hand is now exerting a force upwards that's equal and opposite from this normal reaction force. And this normal reaction force is a force exerted, or should I say, on left hand by right hand. So notice how this is like a normal reaction pair, or a Newton's third law pair. This might not be like the most perfect or accurate explanation, but this is how I think of it.